16, we have a function f. We don't know what f is, but we're told that f prime of x is 2x plus 1. F of 1 is 4. And we have to approximate f of 1.2 using the equation of the tangent line to the graph of the function at x equals 1. Right? So again, line tangent, that's leaving us with the derivative. All right, but equation of a tangent line, that's our point slope form. All right, we want to use the point slope form of our line to approximate f of 1.2. So we need to plug in for x1, y1, and m. All right. Now, x1 and y1 are the given points that the function passes through. And we're told right here, because we're interested when x is equal to 1, we're told that the function's value at 1 is 4. So x1 will be 1, and y1 will be 4. Right, so we have y minus 4 and x minus 1. What we don't have yet is the slope. But we know the slope of the tangent to the curve at a point, that's our derivative. So we have to use our derivative as well. Specifically, we're interested in the derivative when x is equal to 1. So we need f prime of 1. So that's 2 times 1 plus 1, or 3. So 3 is going to go right there. That's our slope, because the derivative is the slope of the tangent to the curve at a point along the way. So there's our slope. Now we're interested in f of 1.2. We want to approximate that using this new equation that we've created, because this tangent line right here that's been boxed off is very, very close to the function when x is equal to 1. All right, so we can figure out how the function is changing by using an approximation for it by using the equation of the tangent line. We have to plug 1.2 in for x. So we have y minus 4 equals 3 times 1.2 minus 1. The only thing we've done is we've replaced x with 1.2. 1.2 minus 1 is 0.2. So we can simplify that. 3 times 0.2 is 0.6. So we have y minus 4 is equal to 0.6. And you can see where we're heading here. We're going to get y all by itself by adding 4 to both sides. So y is, I wrote equals 4.6, but really y is approximately 4.6. And we can see that is answer C. Now we get to problem 17, open response. Part A, for what values of k and p will f be continuous and differentiable at x equals 1? So this is similar to a previous problem that we've done that was multiple choice. All right, continuous and differentiable. So 2x minus x squared must equal x squared plus kx plus p. That's the continuity part. The two parts of the function are equal to each other. In order for it to be differentiable, that we need the derivatives to be equal to each other. What's the derivative of 2x minus x squared? 2 minus 2x. What's the derivative of x squared plus kx plus p? 2x plus k. Now we're interested when x is 1. So if we replace x with 1, we should be able to solve this system of equations. 2 times 1 is 2, 1 squared is 1. 1 squared is 1, k times 1 is k. So we have 1 equals 1 plus k plus p. Over here, when we plug in 1, we have 2 minus 2 equals 2 plus k. 0 equals 2 plus k. So we can see that k must be negative 2. Since k is negative 2, now we have 1 equals 1 minus 2 plus p. We can solve for p. 1 minus 2 is negative 1. Right? So we have that. And we add 1 to both sides. We can see that p is equal to 2. So p is 2, k is negative 2. Find the value of f prime of negative 5 for b. Well, we already did f prime up here, but let's do it again. F prime of x is 2 minus 2x when x is less than or equal to 1, and 2x plus k when x is greater than 1. Well, what's negative 5? Less than or equal to 1 or greater than 1? Yeah, it's less than or equal to 1. So we're going to plug negative 5 into the top part here. So f prime of negative 5 is 2 minus 2 times negative 5, which is the same thing as 2 plus 10, or 12. Part C, write an equation of the line tangent to f at the point where x equals negative 1. All right, so this is our x1 value. We're going back. Y minus y1 equals m times x minus x1. We have negative 1 right here, so we're going to replace x with negative 1. So we have x plus 1 in parentheses. We also have our y and our equal sign. We have to plug in for y1. y1 is the function's value at x1. We have to plug negative 1 into the original function. Where does negative 1 fall? Top of condition or bottom condition? Up here, right? Negative 1 is less than or equal to 1. So we're going to plug negative 1 in for x. Right? So f of negative 1 is 2 times negative 1 minus negative 1 squared. 2 times negative 1 is negative 2. Negative 1 squared is 1. So we have negative 3. That's our y1 value, negative 3. Now we need the slope. The slope of the tangent to the curve at a point. That's our derivative. Right? Well, we have our derivative right here. We're interested in the derivative when x is negative 1. So we want f prime of negative 1. Just like with negative 5, negative 1 is less than or equal to 1. So we're going to use this top derivative. 2 minus 2 times negative 1, which is 2 plus 2. So our slope is 4. And that is our equation of the line tangent to the curve when x is negative 1. Last but not least, find the average rate of change of f over the closed interval from negative 3 to 1. So this is f of 1 minus f of negative 3 over 1 minus negative 3. F of 1, back up, we use the top equation for when x is 1. We plug in 1, we have 2 minus 1. 2 minus 1 is 1. So f of 1 is 2. F of negative 3, right, that's going to be 2 times negative 3 minus negative 3 squared. 2 times negative 3 is negative 6. Minus negative 3 squared is 9. So f of negative 3 will be negative 15. So 2 minus negative 15. Right. In the denominator, 1 minus negative 3, so that's 1 plus 3, just as this is going to become 2. I'm sorry, I wrote 2, I meant to write 1 up here, my bad. Hopefully you caught that. That should be a 1. And we have 1 minus negative 15, so we have 1 plus 15 over 1 plus 3, or 16 over 4, for a final answer of 4.